Hello everyone, my name is Yusuf A. Khan and I am a researcher at Stanford University. Today I'm going to be showing you how to recreate the figure 2 from the article Discovering a Novel Orf coined ORF-Y in the mRNA of POLG. Specifically, we're going to be recreating this SynPlot2 figure. The relevant panels are the bottom two. So essentially SynPlot2, which was developed by Andrew E. Firth at the University of Cambridge, looks at the rate of synonymous substitutions over the course of an open reading frame. In this case, we're looking at the mRNA of POLG. So what you can see here is that we have on our bottom panel the observed rate of synonymous substitutions divided by the expected rate of synonymous substitutions. So when this ratio goes low, that means that we're observing less synonymous substitutions than we'd expect. So that's indicative of an overlapping reading frame, because synonymous substitutions which would not affect one open reading frame would affect an overlapping one. So a lack of synonymous substitutions means that there might be two open reading frames that need to be conserved, but it can also mean other things as well. And then there is a corresponding p-value. So I've attached code in the GitHub page, which will run you through how to redesign this figure. I'm going to look specifically at the mammalian clade. Obviously, the figure has sauropsids, amphibians, and teleost fish, but you can go through that on your own time. So the primary mRNA transcript for Homo sapiens for POLG is this, and this is the corresponding protein sequence. There are actually two primary transcripts that are supported at both APRIS P1 and TSL level 1. I've simply just chosen one. So simply go to tblastn, which I've already done, but I want to just go through it again. tblastn is where you have a nucleotide query, and you're going to get you have a protein query, and it's going to give you nucleotide sequences by searching the 6 translatable frames. So that's our protein sequence, and I've already put my database in, which is the RefSeq RNA, and the clade, which I'm just going to type out again, is just mammalia. And the only other thing we're going to change is the max number of target sequences. We're just going to go up to 500. The only reason I've gone up to 500 is because I want to make sure I get all hits that are above a query cover of 80%. So I've already done this, and you want to sort your results by query cover. And as you can see, we have a bunch of hits, and we have distinctly there's a distinct division between 80% and the rest of the sequences, which is why we went up to 500, which is great. So what we want to do is we want to select all sequences above 80%, which I've already done. You can do this. You can code this to do this automatically, but I've just preferred to do this manually, because when I look at the sequences, I like to just read through them since they're at a manageable level and make sure that there are no odd sequences or sequences that are from, say, another sequence, or another gene or another sequence that shouldn't be in there. So choose sequences that are up to 80% query cover, and you want to download both the GenBank files and the hit table as text. And then in the code, you want to make sure that your BLAST GenBank and your BLAST text output inputs are changed to whatever the file name is, and then the filter list which you're going to use. So for mammals, you want to use the mammal filter list, and so to make sure that you've done that, just control find filter list, and in the code, just make sure in the right CDS and the right protein commands that you've put the mammal filter list if you're looking at mammals. Now that we've downloaded that, you're just going to run the code. The only requirements besides having Python 3 is you need the muscle executable. Whether you're running Windows or Unix systems, the code is operating system agnostic, so it doesn't really matter. Just put the path for that, and then you need to have Tranoline, which is in the Memboss suite, and the Python. In addition to Python, you need to have BioPython installed. So simply, I will run the code because I've already downloaded all of these, and I'm just going to run it, and I'm going to generate. Essentially what this does is I'm generating, after I filter the sequences, I'm generating a translationally aligned, which means that the nucleotides are aligned at a codon level of the nucleotide sequences after I've filtered them and aligned them and such. And what we're going to do after that is I should run this last part. What we're going to do is we're going to run the simplot2 code. Now, simplot2 is written in R, but I'm just being lazy, and I'm just going to the online database, which is right here. Just because it's a bit more of a visual representation and easier to run through. The file we want is this channel line output. So instead of running code, I'm just going to copy and paste this into the submission. And our reference is going to be Homo sapiens, and sliding window, recommend using the default 25, but obviously, feel free to change it depending on if you're looking at a different sequence. And so hopefully we should be able to recreate this simplot. Brilliant. So as you can see, we've recreated the simplot figure. There's just a prettier version of it.